70 million years ago, the oceans did not belong to whales. They belonged to something that had once walked on land. If a modern human were dropped into those waters, survival would not be measured in hours, but in heartbeats. The late Cretaceous sea was not empty blue space. It was a dense energy network, warm, mineral-rich, thick with plankton blooms that fed fish, that fed reptiles, that fed giants. Continental plates sat lower. Shallow inland seas split continents in half. Temperature gradients were mild. Oxygen levels fluctuated. Coastlines shifted with tectonic indifference. This system required no mammals. Within this marine engine moved the mosasaurs, apex predators engineered by evolution from terrestrial squamates, distant relatives of monitor lizards and snakes. Their limbs had restructured into hydrofoils. Their tails expanded into crescent propulsion blades. Double-hinged jaws allowed prey to be swallowed headfirst, resisting escape in 3 dimensions. Level 1 threat was the sea itself: pressure, salinity, currents that erased orientation. Level 2, predatory fish and smaller mosasaurs competing for biomass. Level 3, giants like Mosasaurus hoffmanni, exceeding 14 meters, capable of dismembering armored ammonites and sea turtles with conical, bone-crushing teeth. Level 4 was climate. Ocean chemistry shifted. Volcanism altered temperature, productivity pulsed and collapsed. In this equilibrium, a human body is soft tissue. The ecosystem does not recognize fear. It recognizes caloric opportunity. Mosasaur evolution did not begin in deep water. It began in coastal margins, estuaries thick with sediment, tidal flats, where land predators tested brackish thresholds. Fossil sequences from the early Late Cretaceous show transitional forms, such as Dallosaurus, retaining weight-bearing limbs while exhibiting elongate bodies and laterally compressed tails. Bone microstructure reveals a shift. Dense limb bones for walking give way to lighter, more porous architecture optimized for buoyancy control. The skeleton records a migration from gravity to suspension. The western interior seaway, which split North America in 2, became a laboratory of scale. Warm, shallow, and biologically productive, it functioned as a conveyor belt of nutrients. Ammonites spiraled through mid-water columns. Hesperornithine diving birds hunted fish near the surface. Early sharks traced chemical gradients below. In this layered system, mosasaurs diversified rapidly. Their skulls lengthened. Quadrate bones loosened to permit jaw expansion. A secondary row of pterygoid teeth lined the palate, preventing prey from backing out once seized. Stomach contents preserved in fossil specimens confirm a diet that included fish, turtles, seabirds, and even other mosasaurs. Toothwear patterns indicate repetitive high-force impacts, shell-crushing, bone-shearing. Level 1 pressure remained constant, buoyancy regulation, and thermoregulation in variable waters. Unlike modern whales, mosasaurs were reptiles. Isotope analysis of tooth enamel suggests some degree of elevated metabolic control, yet still constrained by external temperature. A human entering this system would face hypothermia before predation. Salt imbalance would degrade neuromuscular coordination. The ocean does not negotiate adaptation. It filters it. Hydrodynamics governed survival long before teeth made contact. The mosasaur body was not simply elongated, it was restructured around thrust efficiency. Early reconstructions imagined eel-like undulation along the entire spine. More recent fossil evidence, particularly preserved tail impressions from specimens such as Prognathodon, reveals a downward bend near the tail's end, supporting a crescent-shaped fluke. Propulsion concentrated in the posterior third of the body, reducing drag and stabilizing pursuit trajectories. Rib cages narrowed toward the hips, limbs shortened into rigid paddles with limited independent articulation, functioning more as stabilizers than drivers. The vertebral column stiffened in key regions, redistributing mechanical stress during acceleration. This was not improvisation. It was iterative refinement under selective pressure. Level 1 threat within this architecture was energy expenditure. Large marine reptiles required constant intake to offset heat loss and locomotor demand. Miscalculated pursuit meant caloric deficit. Level 2 threat emerged from competition. Other mosasaur genera, Tylosaurus, Clydastes, Platecarpus, occupied overlapping niches, differentiated by skull robustness and prey preference. Bite-marked fossils indicate intraspecific combat and cannibalism. Level 3 was ambush failure. A wounded mosasaur bled into a column already patrolled by sharks, such as Cretoxorhina. The water did not pause for hierarchy disputes. Level 4 remained invisible. Oceanic anoxic events. Sediment cores show intervals where oxygen dropped sharply, collapsing fish populations. Apex predators cannot persist without base productivity. A human body introduced here would struggle before contact. Lung capacity limits dive time to minutes. Panic accelerates oxygen depletion. In open Cretaceous water, exhaustion is not dramatic. It is procedural. Vision in the Cretaceous sea was filtered through suspended life. Light attenuated quickly in nutrient-rich waters, fragmenting into green-blue gradients. Mosasaur eye sockets were large relative to skull size, suggesting reliance on acute visual tracking in dim conditions. Scleral ring structures, preserved in some specimens, imply structural support for pressure adaptation. This was not deep abyssal hunting, but mid-column pursuit where silhouettes determined survival. Olfaction functioned differently than in terrestrial reptiles. Water carries chemical signals in diluted trails. Forked tongues, inherited from squamate ancestors, likely sampled gradients to triangulate wounded prey. The palate teeth, rearward pointing, recurved, formed a biological ratchet. Once prey crossed the threshold of the jaws, escape vectors narrowed to zero. Level 1 threat remained environmental opacity. Suspended sediment from storm runoff could reduce visibility to meters. In such conditions, collision risk increased. Level 2 threat came from armored prey. Ammonite shells display puncture patterns consistent with failed crush attempts. Broken teeth found alongside them indicate that predation was costly. Level 3 threat emerged from equally scaled rivals. Fossilized mosasaur vertebrae bearing embedded teeth confirm that combat occurred at full force. Level 4 was seasonal instability. Stable isotope data from marine sediments record fluctuations in sea temperature tied to volcanic outgassing and shifting currents. Productivity oscillated accordingly. A modern human placed here would misjudge distance underwater. Saltwater refracts light, distorting depth perception. Emuscular strikes slow in dense fluid. In an ecosystem calibrated for hydrodynamic precision, hesitation is measurable, and measurable error accumulates quickly. Reproduction did not occur on beaches. Unlike sea turtles, mosasaurs did not return to land. Fossil evidence from gravid specimens and embryonic remains indicates live birth in open water. This adaptation severed the final dependency on terrestrial substrate. The life cycle closed entirely within the marine column. Juvenile mosasaurs, smaller and more vulnerable, occupied different ecological strata than adults. Tooth morphology in young individuals suggests softer prey, small fish, and cephalopods, reducing direct competition with larger conspecifics. Growth rings in bone histology reveal rapid early development, an evolutionary response to predation pressure. Survival required acceleration through vulnerability. Level 1 threat for juveniles was scale mismatch. The sea contains few sanctuaries. Level 2 threat included predatory fish and larger mosasaurs. Stomach content analysis confirms cannibalism. Level 3 threat emerged from ecological overlap zones, where resource scarcity forced interaction between age classes. Level 4 pressure remains systemic. Shifts in plankton productivity cascade upward. When microfossil abundance declines in sediment layers, vertebrate fossil frequency follows. The base controls the apex. A human newborn requires extended parental care measured in years. Mosasaurs required metabolic independence within months. Introduce a human infant into this system, and survival probability approaches statistical noise. Even an adult human, deprived of shelter and thermal protection, would face rapid core temperature decline. And saltwater conducts heat away from the body approximately 25 times faster than air. The Cretaceous ocean did not nurture weakness. It selected against it. Predation in the Late Cretaceous Sea was not chaotic violence. It was mechanical exchange. Bite force estimates derived from jaw lever modeling suggest that large mosasaurs generated pressures sufficient to fracture turtle carapaces and ammonite shells. Tooth cross-sections reveal thick enamel and robust dentine cores, optimized for resisting torsional stress during twisting strikes. Some genera, such as globidans, evolved rounded molary-formed teeth specifically for crushing hard-shelled prey. Others retained sharper conical dentition for piercing fish and soft-bodied reptiles. Niche partitioning reduced direct competition, but overlap remained inevitable. Level 1 threat was structural failure. A cracked tooth in a marine predator compromises feeding efficiency. Fossil jaws show healed fractures, evidence that injury was common but survivable if infection did not set in. Level 2 threat was prey defense. Large turtles bore scars. Some ammonites survived partial predation attempts. Level 3 threat emerged from size asymmetry. A 14-meter mosasaurus encountering another of similar scale faced mutual lethality. Embedded teeth in vertebrae confirm that some encounters ended in bone penetration. Level 4 pressure lay beyond combat. Long-term oceanic chemistry. Carbon isotope excursions near the end of the Cretaceous indicate disruptions in the global carbon cycle. Food webs thin when primary productivity destabilizes. A human rib cage fractures under far less compressive force than a Cretaceous turtle shell. Lung collapse under sudden pressure, salt aspiration, and rapid blood loss would follow a single high-force bite. Yet predation is not required for death. Dehydration occurs even while surrounded by water. The body cannot process salinity at that scale. Physiology fails quietly before violence becomes necessary. Evidence of mosasaur dominance is written in stratigraphy. Marine sediment layers from Europe and North America repeatedly yield articulated skeletons, tooth scatters, and coprolites, rich in bone fragments. Stable oxygen isotopes extracted from tooth enamel suggest partial endothermy. Body temperatures maintained slightly above ambient seawater. This metabolic flexibility allowed expansion into cooler latitudes, widening territorial range beyond strictly tropical bands. Comparative morphology shows convergent evolution with later marine predators. The tail fluke mirrors that of modern sharks and whales. Limb reduction parallels ichthyosaurs. Yet mosasaurs were neither fish nor mammals. They were reptiles occupying a hydrodynamic solution refined independently. Evolution does not prefer identity, it prefers efficiency. Level 1 environmental stress persisted as fluctuating sea levels. Transgressive and regressive cycles altered coastline geometry, compressing habitats. Level 2 stress involved prey migration. Shifting currents redistribute biomass. Level 3 stress intensified with interspecies overlap as ecological zones narrowed. Level 4 arrived from beyond the ocean itself. At the Cretaceous-Paleogene boundary, a bolide impact injected aerosols into the atmosphere. Sunlight diminished. Photosynthesis collapsed. Plankton populations fell sharply. Without primary producers, trophic pyramids inverted. Apex predators cannot outswim starvation. In a collapsing marine food web, a human fares no better than a mosasaur. oxygen levels fluctuate. Toxic blooms increase. The difference is scale, not outcome. Both are bound to the same energy chain. The ocean that perfected mosasaur design also erased it. Evolution is not loyalty. It is conditional continuation. The extinction horizon is visible as a thin, darkened layer enriched with iridium, an extraterrestrial signature embedded within marine sediments worldwide. Above it, mosasaur fossils disappear. Below it, they are common. The transition is abrupt in geological terms. What dominated millions of years can vanish within thousands. Planktonic foraminifera show drastic reduction in diversity across this boundary. Without microscopic primary producers, carbon fixation declines. Surface waters cool as sunlight is obstructed by atmospheric particulates. Food chains fracture from the base upward. Large-bodied predators, dependent on continuous intake, face immediate deficit. Level 1 collapse was productivity loss. Level 2 collapse involved prey extinction. Ammonites and many fish lineages disappeared simultaneously. Level 3 collapse targeted apex predators already stressed by shrinking habitats. Level 4 collapse was systemic. Global climate oscillation, acidified oceans, disrupted currents. Mosasaurs were not defeated by a superior hunter. They were removed by thermodynamics and planetary mechanics. No jaw strength counters sunlight deprivation. No fluke outruns chemical imbalance. Introduce a modern human into that same terminal phase. Food scarcity, toxic waters, unstable temperatures. Survival probabilities align closely with those of any large vertebrate. Technology may delay exposure, but dependency on photosynthetic energy remains absolute. The Cretaceous ocean functioned as a closed equation. When input variables changed beyond tolerance, solutions ceased. Mosasaurs were not failures. They were precise answers to specific conditions. When conditions shifted, precision became irrelevance. In reconstructed museum halls, mosasaurs appear suspended in perpetual motion, jaws open, tails curved, teeth exposed in static aggression. Yet the fossil record presents them differently. Disarticulated vertebrae scattered by currents, tooth marks on bone from post-mortem scavenging, skeletons partially dissolved by sediment chemistry before burial completed preservation. Even in death, the system processed them efficiently. Their rise illustrates how rapidly evolution can exploit ecological vacancy. Their disappearance demonstrates how little permanence dominance provides. Apex status depends entirely on energy throughput. When plankton density declines, when ocean temperature crosses metabolic thresholds, when acidity interferes with shell formation at the base of the web, scale becomes liability rather than advantage. A human body placed into the late Cretaceous ocean would not confront a villain. It would encounter a calibrated environment. Salinity near 35 parts per thousand disrupts hydration balance. Core temperature drops steadily in open water. Visual range shortens with turbidity. Beneath the surface, pressure increases by 1 atmosphere every 10 meters. Physiology yields to arithmetic. Mosasaurus and its relatives were not monsters. They were expressions of marine optimization, reptilian lineages that surrendered land for hydrodynamic authority. For millions of years, the equation held. Then the boundary layer formed, thin and indifferent. Modern oceans are different in species, not in principle. Energy still governs structure. Adaptation remains conditional. The sea does not remember mosasaurs. It does not anticipate humans. It only maintains balance until balance becomes impossible.